Welcome to a lesson with Dr. Powell. We're going to take a little look at exponential functions and logarithmic functions and how they graph. First of all, let's look at the graph of y equals 2 to the x. Now, I'd like to think about analogies here. For every one you go over, you add one to the exponent, which is like multiplying by 2. X plus 1, addition of exponents becomes 2 to the x times 2. So for every 1 over, you multiply by 2. 1 over, multiply by 2. So 1 over, expand, multiply by 2. So instead of adding by 2 each time, you're multiplying by 2. So I might even think of this 2 as being like a multiplication slope. For every one of 1, you're multiplying by it. Well, that's quite telling because just like we have something like y equals mx plus b, let's just convert this plus to multiplication. So repeated addition. See this multiplication? Let's do repeated multiplication, which is exponentiation. So we have m to the x instead. This is really the format of an exponential function, where, again, this is the intercept. This is like the multiplication slope. So, for instance, if I had the graph, if I had 5 times 2 to the x, then I'd know how to graph this. This is the y-intercept. I can get it just by plugging in 0. That works too. But yeah, that's the y-intercept. And then I know that every time I go 1 over, it's multiplied by 2. So I get some really steep growth here for this function. That's what exponential functions are. And if I go backwards, I divide by a fifth, divide by a fifth, divide by a fifth, divide by a fifth, or divide by 5. Sorry, I multiply by a fifth, multiply by a fifth. That's what I meant to say. Multiply by a fifth going back this way, and it gets smaller. Okay, so that's an exponential graph. Now, how do we think about a logarithmic graph? We draw our line to reflect across y equals x to switch x's and y's place in order to get the inverse function. So if an exponential function looks like this, a logarithmic function will look like this. Notice its domain is starts right here from 0 onward. Log with any base. This would be a graph. And notice that the log any base of 1 is just 0. I mean, is just 0. Just like here, for instance, if we take 2 to the 0, we always get 1. And if we reverse that, 1 goes to 0 every single time. But this is really nice. 3 to the 0 goes to 1 as well. So, but this diagram would go back the other way. So here, if you plug 1 in to any log base, you always get 0. So if you just had a log graph, like y is equal to log base something or other, let's just do 7, that's fine. Then it would look something like this. Exponential growth is steep and swift, and logarithmic growth does eventually get extremely large. In fact, it keeps on going up and up forever, but just goes very slowly. And whereas exponential growth is extremely quick. So this is the basic graph of a logarithm. It's important to remember what that basic graph is. We can do some transformations of these graphs. For instance, why don't we try one with log? Why don't we do log base, let's do log base 3 of x plus 1, and maybe like minus 2. Let's look at this graph. What would this look like? Well, first, let's look at the graph of log base 3. Log base 3 naturally will follow the logarithmic form right here, where that's 1. something like this. If you want to get an extra point on it, just kind of turn your head and imagine that this is an exponential on its side. And then when we would plug in 1 into that exponential, we'd get out 3, right? So we get a point, if you like. Okay, so that's what it is. But then from here, this tells us shift to the left 1. So we just shift that over 1. So now it would be like that kind of, I guess. And then this says shift it down 2 from there. So maybe down to here. And this down to, so something like that roughly. And that would be our final graph. Thanks for watching.